Hello everyone. In this video, I'm going to be talking about how to write a mechanism for a Fischer esterification. This reaction obviously involves an acid. So we have a carboxylic acid functional group, and you can have any R groups down there. You can have this particular one just an glacial acid, but you could have some other form of carboxylic acid and a combination with an alcohol. So you could have any sort of alcohol going from methanol all the way to maybe propanol or even pentanol or some other ones as well. And this is going to be done in the presence of a concentrated acid, most likely sulfuric acid. So you use that in a catalytic amount. So when we say in catalytic amount, maybe 3 to 4 drops of those will be good enough. And since it's going to be acting as a catalyst, we use it, but we will retrieve it at the end of the day. Eventually, it's going to make an ester. So the way it makes an ester, we're going to have uh, this part right here. Just going to go ahead and draw that. It will make a new bond. So here is going to be the new bond, and I'll show you that in the mechanism. And we're going to have the alcohol part right here. So this is how exactly the ester is going to look like in this particular case. Along with that, it's going to make water. Okay, so the water is technically coming from this H here and this OH right there. So that's those two together makes the water. This reaction actually sets up an equilibrium, even though it's in a product favor, but it still have a tendency that you will have some of the reactants unreacted, so it never really goes to the completion. If you want to make sure you have the most product, you can do one of the two things. You can either go ahead and have one of the reactants in excess, and typically it's acetic acid or the carboxylic acid that's going to be in an excess because it's relatively cheaper when you do that in the lab. And then the other thing you can do is as soon as the H2O is made, you want to kind of get rid of it. And one of the ways you can get rid of it, you can add some molecular sieves, or maybe you can add some drying agent. So as soon as this is made, it absorbs the water so it can shift the equilibrium to the right side. But obviously, we're not really talking about, the equilibrium effect here. We're just going to be looking at how the mechanism really work in this particular case. So obviously, we're going to be going ahead and starting with our carboxylic acid in terms of equilibrium, and we're going to be using the sulfuric acid here to protonate that carboxylic acid. So we're going to have this sulfuric acid here that looks like this, and we're going to be going ahead and protonating that oxygen. So we're going to use that oxygen to grab this proton, and this comes up here. So in the process, I'm just going to go ahead and copy that down. So this process makes, go ahead and protonates that oxygen. So we'll use obviously one of the lone pairs there. So we still have one lone pair left there. We'll have this protonated. This gets a positive charge. And along the way, it's going to make this conjugate base of the sulfuric acid. So this conjugate base is going to have an O minus there. That's one way of writing it. The other way of writing it, I can also write that as an HSO4 1 minus. So I'll probably go ahead and write that as an HSO4 as we move along. Now this is an acid-base reaction, so very well this is going to be an equilibrium reaction. You may see that in equilibrium in this in the books. So the next step is going to be the nucleophilic attack. So as soon as this was protonated, this carbon becomes even more electrophilic. Now you're going to have a nucleophile coming in, and obviously your nucleophile is your alcohol here. I'm going to go ahead and bring that in and have this alcohol doing the nucleophilic attack on here. So we're going to be using the oxygen here to do the nucleophilic attack. So you want to make sure you draw in a curved arrow here. This does the nucleophilic attack. This comes up here. Just going to go ahead and copy that down right here. And we do make one new bond now. So this is going to be your new bond. Maybe we can draw that with a different color. So that's your new bond. And then we're going to have our oxygen and go ahead and draw the rest of the form here. So we this still have the hydrogen uses one lone pair, so this oxygen gets the positive charge. You want to make sure you're conserving the charge as you're moving along as well in this particular case. The next step is more or less going to be in a proton transfer. So when you run the proton transfer, there's a few ways you can do it. You can run it with sulfuric acid, or you can run it with alcohol that you already got in there. So either one of those ways are actually going to be fine. And so to run that proton transfer, I can be like, okay, I'll go ahead and use my alcohol here. And this alcohol would go ahead and grab this proton, restore the electron density back onto the oxygen. So then this is how it's going to look like. All right, and then in the next step, we are going to be, obviously, maybe I can just redraw this as well here. So this is going to be getting protonated here. So with a positive charge on that oxygen. So then I can go ahead and run this proton transfer again in this next step where I would be protonating one of the oxygens. It doesn't really matter which oxygen you protonate out of those two OHs here, but I want to be protonating one of those so that I can have a good leaving group. So let's suppose I go ahead and protonate this oxygen here so I can have a good leaving group. Right now the OH is a bad leaving group. And that restored electron density back onto that oxygen. So like I said, you may have used the HSO4 as well, and then you would make an H2SO4 here, and then you use that to protonate that oxygen. So it doesn't really matter what you really use as long as you're using some of the bases or the conjugate bases in there. So this will end up having two protons now with a positive charge. So now all of a sudden this is actually a relatively good leaving group. So now what I really want to do is I can go ahead and use my lone pair on the oxygen. So remember this oxygen has actually two lone pairs. I've been drawing only one. Um, so when I go back and have this lone pair going back in there, this will get knocked out. So once this gets knocked out, we will end up getting, probably I can just draw that, an oxygen there. And I'll keep the colors coordinated. So we have this bond right there, and you got the oxygen right here with an isopropyl group right there, and then still have this hydrogen intact right here. So that oxygen gets a positive charge, and obviously you have lost the water here. So that water was actually one of the products that you have seen in the reaction, in the overall reaction. So that's how you make the water here. And then eventually to get to your final product there, I would have to retrieve my acid back. So to retrieve my acid back, I want to do one more acid-base reaction at the end of the day. So this is, you can treat that as a reversible reaction again because it's just an acid-based reaction. So where I would use HSO4 1 minus that you have actually retrieved here. And I want to go ahead and use the lone pair from that. And obviously you can draw the structure, but I'm not really going to draw the structure here. So this lone pair from the oxygen on that um, uh, hydrogen sulfate ion is going to go grab the proton and it's going to restore the electron density back onto that. And that makes the ester at the end of the day. And obviously that's going to make an sulfuric acid along with it. Obviously, you don't really write the sulfuric acid in an overall balanced equation because it's in a catalyst, but you must retrieve it before the mechanism is over.